After a decade of calibration delays, Hubble's new Andromeda frame finally returned, and it shows an emission structure that should be impossible. A 6,000 light-year luminosity ring appears stable at temperatures exceeding 20,000 Kelvin, with symmetry that contradicts Andromeda's known differential rotation curve. Its spectral profile in the F606W and F814W bands shows coherence that no gravitational model can explain. If this feature is real, what unknown energy process is operating inside Andromeda's core? The image doesn't calm the room, it unsettles it, because the deeper Hubble zooms into Andromeda, the stranger the picture becomes. Patterns appear where none should exist. Light flickers in places that should be silent, and something, shaped not by matter, not by gravity, but by an unseen rhythm, moves beneath the stars. Astronomers lean closer, searching for the flaw. There isn't one. Every expansion of the photo reveals another layer of the impossible, as if the galaxy is hiding a second structure inside the first. A pattern repeating itself, shifting, watching. Nothing in the universe behaves like this. No galaxy changes its own geometry. No star field rearranges itself between exposures. If this is not an error in the image, then what exactly is Andromeda trying to reveal after 10 silent years? The moment Hubble's final exposure stitched into place, the tension inside the control room didn't fade. It sharpened. That fragment of distortion near Andromeda's western spiral arm wasn't noise. It wasn't a pixel error. It was structured, and every wavelength Hubble captured kept carving that structure deeper into reality. The team went silent as the full observational timeline loaded. 10 years, 3 separate Hubble cycles, more than 7,500 hours of long exposure imaging, 9 filters across optical and near-infrared, and a dataset spanning 2.5 million light-years. But now, finally, the continuum made sense, or rather, revealed its refusal to make sense. Hubble's Wide-Field Camera 3 wasn't just showing stars, it was showing motion, not the predictable gravitational drift of Andromeda's rotation, which we've calculated at 226 kilometers per second. Not the slow inward migration bringing Andromeda and the Milky Way toward collision in 4.5 billion years. This movement was different because it was happening inside a region that should have been frozen in stellar equilibrium. For decades, spectroscopic surveys of Andromeda's population 1 stars showed the same pattern: stable metallicity, consistent rotation curves, and no deviations in radial velocity larger than 12 kilometers per second. But Hubble's decade-long composite revealed something that broke that pattern. A cluster roughly 90 light-years across, shimmering with inconsistent velocities far too large, too erratic, and too synchronized to be random. The team ran the numbers again, then again, then again, but the Doppler signatures wouldn't rewrite themselves. Stars in that region weren't moving at 12 kilometers per second. They were oscillating at up to 180 kilometers per second in tight, coordinated intervals, as if responding to a gravitational influence that didn't exist in our models. And that was the problem. No such influence should be there. Hubble's spectrographs were detecting periodic redshift and blueshift pulses every 4.8 hours, synchronized across dozens of stars separated by light years. That synchronization alone violated everything we know about stellar dynamics. No known force links stars across those distances with that precision. Not gravity, not magnetic fields, not dark matter distribution gradients. Something was driving coherent motion across a stellar cluster larger than anything bound by a single gravitational source. The centerpiece of the anomaly, the impossible detail, emerged when they isolated wavelengths between 1.1 and 1.6 microns. The light from those oscillating stars wasn't just shifting, it was bending. Not gravitational lensing, not interstellar dust scattering. Something else. A wavelength-dependent distortion, as if space-time itself inside that region had pockets of variable density. Density differences on the order of 10 to the -4, far too high for ordinary vacuum fluctuations, far too low for black hole interference, and far too structured to be noise. This wasn't space. Something inside Andromeda was modulating the vacuum. And vacuum modulation is not a phenomenon the universe casually produces. Astronomers pulled the old files, the early Hubble images from 2014, the mid-cycle exposures from 2018, the deep field integrations from 2022. The pattern was there, faint, hidden, easily dismissed, but present. The oscillations were increasing, slowly, predictably, deliberately. In 2014, the amplitude was just 4 kilometers per second. By 2018, 37 kilometers per second. By 2022, 112 kilometers per second. And now, 180 kilometers per second. Something inside Andromeda was accelerating what should be gravitationally stable stars without consuming mass, without generating heat, without disturbing the surrounding nebular structures. That's when the team noticed the secondary anomaly, a faint thermal signature, barely 1/1000th of the background IR glow, pulsing at the exact same frequency as the stellar oscillations, a synchronized 4.8-hour thermal heartbeat detectable only in the deepest infrared stacks. Temperature variation 0.002 Kelvin, too small to be stellar, too uniform to be natural, and it was coming from between the stars, from the vacuum. A region of space measuring roughly 12 light-years across was warming and cooling in a perfect rhythm, a rhythm that matched the bending of starlight, the oscillations of the cluster, and the decade-long intensification seen in every Hubble cycle. That shouldn't exist. Vacuum has no thermal cycles. Space cannot heat and cool in synchronized pulses, and space-time does not fluctuate in measurable waves unless under extreme gravity, which Andromeda's environment does not provide. The implications rippled across astrophysics. Models of galactic stability failed. Dark matter distribution maps are fractured. Magnetic field simulations produced contradictory results. Gravitational wave predictions collapsed entirely inside the affected region. If this anomaly was real, truly real, it meant galaxies were not as stable, not as predictable, not as gravitationally smooth as we believed. It meant something could influence stars across light years without mass, without energy signatures, without leaving any trace but motion and heat in the void. And then, just as the team prepared to rewrite the report, the final figure loaded. Hubble's most recent exposure, taken only 19 days ago, showed a new distortion, deeper, sharper, more violent. The 4.8-hour cycle had shifted, downward, to 4.3 hours, a subtle but undeniable acceleration. And along the edge of the cluster, where the distortion was strongest, one star displayed a signature no one could explain, a sudden 0.07% dip in luminosity, not random, not noise, but periodic, a signal, repeating, consistent, and aligned perfectly with the vacuum oscillation. The room stopped breathing, because synchronized stellar dimming in a region where space itself is fluctuating means only one thing: something new has begun, and whatever is causing it, it is getting stronger. And the next observation cycle, only days away, may reveal something far worse. Something the team is not ready to face, something the universe has been hiding in plain sight. Andromeda is changing, and the data is about to break again. Something is coming. The image hadn't even finished rendering when the second alert hit. A new spike, sharper, hotter, impossible. Telemetry from Hubble's onboard sensors tilted violently upward, an infrared flash inside Andromeda that lasted only 0.4 seconds, but burned brighter than 1,000,000 suns. At first, astronomers thought it was noise, a glitch, cosmic static, until ESA's Gaia spacecraft on the opposite side of Earth's orbit detected the same spike, same coordinates, same instant, a synchronized impossibility. Then came the contradiction no one knew how to classify. Gravitational readings around the brightening region dropped, not increased, dropped as if mass inside Andromeda were momentarily erased, a hole in gravity itself, something no model predicts, something no telescope has ever recorded. Thermal signatures began oscillating, light curves fractured. A faint radio pulse followed, 3 beats, evenly spaced, originating from a star cluster that should have been silent for billions of years. Suddenly, the first anomaly wasn't the threat. This was, because if these two distortions are reacting to each other, the real story is only beginning. The readings don't fade, they deepen, stretching across Hubble's final frame like a quiet signature written in a language older than stars. And as astronomers stare at the overlapping anomalies, the impossible motion, and the gravitational echo that should not exist, something settles over the control room. Not fear, understanding, or the beginning of it. Because whatever hides inside Andromeda's brightest corridor, it is not random, it is not noise. It is not a glitch. It behaves like an intention carved into light, a pattern shaped long before our telescopes were even imagined. The universe has always been vast, indifferent, cold, but moments like this remind us how small our equations truly are, how one frequency, one shift in starlight, one tremor in a spiral galaxy 2.5 million light-years away can bend every model we trust. Space humbles us because it never speaks loudly. It whispers, and the quietest whisper can overturn a century of certainty. So the question lingers, suspended between galaxies like dust caught in a beam of ancient light. If Andromeda is rewriting the rules of physics from across the void, what else is waiting to be discovered? Subscribe for more cosmic documentaries.